Yeah, thanks everyone. My name is Josh Taillon. I'm coming to you from NIST in Boulder, Colorado. I'm here to talk about a project that I have been a part of for probably over a decade now, as both a user and contributor. So I'm here on behalf of a whole maintenance team to reintroduce HyperSpy to you. We had a member here in 2016, and by here I mean in Austin. That was, I think, the first time HyperSpy had been presented at SciPy, but we generally haven't had a huge presence here. So I'm really excited to be able to share what we've been up to. I work for NIST, and so I have to put up this kind of standard disclaimer that opinions are my own. I am not the US government, et cetera, et cetera. Also, separately, these are my opinions and not all of the maintainers' opinions. Of course, when you have a distributed project like that, I don't speak for everyone. So who is everyone? There are literally dozens of us that have contributed to this project over the years. I want to point out in particular the ones in bold here. These are kind of our core development team. Currently, Francisco is De La Pena. This is his brainchild from way back when. He's kind of our BDFL role currently. Eric is our really core maintainer. He does a lot of the day-to-day work on maintaining the package. Also, Jonas and Carter has been a very active developer recently. I'm somewhere down here. I have contributed to the package. I've done various things over the years. These days, I spend a lot more time kind of on the community side of things, doing tutorials, doing things like this. So I don't contribute day-to-day so much to the code, but I'm still involved in the community. And I just wanted to thank Francisco because I'm using some adaptations of some of his slides in this presentation. Who am I? Why am I here? I'm a materials data scientist at NIST. That is a made-up job title. It doesn't actually exist. But what that means is I combine material science and data science together and work with, I think of myself as an internal data consultant within NIST. So I work with researchers to address a lot of any sort of data science, data engineering, data management, all of those sorts of problems that people have in the research world. My background is in materials characterization, particularly electron microscopy. I have done all of these acronyms in the past. If they don't mean anything to you, that's totally fine. As I said, I regularly use and am sometimes maintainer of the HyperSpy project. I'm a software carpentry instructor as well. I really enjoy teaching people how to do things and teaching people how to use new tools. And I've led a bunch of HyperSpy tutorials and Python tutorials throughout the years. So hopefully I'm well qualified to speak with you. As I mentioned, Tomas had presented about the HyperSpy project back in 2016. We've had quite a bit of development since then. He had a much more metal title than I did. It was like how to bend data to your will, which I thought was really awesome and inspired me. But I'll be back. So anyway, what I'll be talking about, I'll introduce HyperSpy, what it can do, what has been done with it. In particular, I wanted to talk a little bit about how we foster community within the HyperSpy project. We are a pretty well-established and mature community, but we're not huge. We're not, nearly as big as some of the projects that you see here at SciPy. And then I wanted to talk a little bit about our recent 2.0 release, which, if I had known all of this stuff about the NumPy 2.0 release was happening at the same time, I probably could have made a good joke, but I don't know. We impacted many fewer people than NumPy when we did our 2.0 release. I'll put it that way. So what is HyperSpy? It is open source, of course. It's a Python library, and it's designed for the interactive analysis of multidimensional data arrays. And it provides robust tools to navigate those data arrays, visualize them, do things like curve fitting and pattern recognition, all within high-dimensional data sets. And it strives to make it as easy to work on multidimensional data as it is to work on, say, a single spectrum or a single image. I also like to describe HyperSpy as a vibrant and welcoming community of users and developers. I think that's just as important as the technical tools that we provide. We aim to produce well-documented tools that are powerful and hopefully easy to use and have a pretty low barrier to entry. HyperSpy originated in the analytical electron microscopy community, but over the years has evolved into a more general-purpose multidimensional analysis tool. We have some guiding principles. At some point, we sat down and said we should have a mission and all of this. But the main thing is our principles here is to be open source, to be community-driven in our development, to be thoroughly documented, to try to ease that sort of cost of entry to new users, to be powerful and scalable, so to make it easy to do complex things as it is to do them on simple things, with a very readable, efficient and consistent syntax throughout the entire application. And then also implementing a modular structure to make HyperSpy easily extendable to make it apply to whatever your particular domain application might be. So when we think about multidimensional data sets in HyperSpy, one of the really core concepts of HyperSpy is dividing those axes, those multiple dimensions, up into what we call two families of axes. We call those signal axes and navigational axes. There's fundamentally no difference between them. This is just a conceptual mental model that's used throughout the application to sort of orient yourself well. If you have, say, a three-dimensional data set, I'll use as an example, where you have a collection of spectra that you collected over a range of X and Y locations, you can think of that as both a two-dimensional array of one-dimensional spectra, or you could think of it as a one-dimensional array of two-dimensional images, right? You could transpose sort of your frame of reference for that data set, and it's still the same underlying data, but you think about it in a different way. So we use that to represent, like we use navigation and signal dimensions to represent how we, that the signal dimension holds the quantity that you are measuring in whatever way. So that could be a spectrum, it could be an image, and then you navigate over whatever set of parameters you were changing when you collected that data. So if you're rastering a beam back and forth, that could be a two-dimensional image, it could be a single line scan, it could be 4 dimensions, so on, so on. This type of multi-dimensional data set is very prevalent throughout the materials characterization community, but it's prevalent through all of science. We do hyperspectral, remote sensing does hyperspectral imaging. MRI imaging is multidimensional. It's everywhere in science. Just some examples of what we see in analytical characterization. I kind of think of it as regular imaging and scanning probe modalities. That's kind of the two ways that I break it up. In this case, in regular imaging, our signal dimensions are the actual X and Y physical dimensions that we're sort of imaging over. And then you could have a regular image, in this case just a picture, right, has no navigation dimension. It's just its navigation axis is 0, and it's just one picture. But you could also take pictures over a range of different energies, right? That would be something like hyperspectral imaging, where you have different wavelengths corresponding to different positions in your data set. I don't have figures for these, but time series imaging could be another example of a one-dimensional navigation axis where you have two signal axes. Tomography is another one where you take images at a range of different tilts, and you do that in order to build up a three-dimensional representation of your data. When we get into what we would call the scanning probe modalities, we get into a world that in materials characterization we often call spectrum imaging, and that's where you're collecting some sort of spectral data. That could be energy dispersive spectroscopy, it could be electron energy loss spectroscopy, it could be any number of types of spectroscopic techniques that tell you something about what's going on in your sample, and you collect either a single spectrum, you collect them along a line, right, if you're probing an interface or a surface or something like that, or you could collect them along a two-dimensional grid, right, where you have now a three-dimensional data cube like I displayed earlier. You could even go to 4 dimensions, where you start collecting images at every pixel that you're rastering across. This is something that's sort of actively developing in the TEM community, which is called 4D STEM, because you have X and Y physical dimensions, and then you have the KX and KY diffraction dimensions, which are what you're actually imaging. So you have 2 navigation dimensions and then 2 signal dimensions. You could imagine doing this as a function of time or as a function of tilt as well. So you could get up to a 5-dimensional data cube or a 6-dimensional data cube. How do you work with these? That is kind of hard to visualize on a 2-dimensional screen. That's what HyperSpy is all about. So in HyperSpy, to represent this data, we use something that we call the signal class. We have the very base level signal is called a base signal. You don't have to be able to read this figure, it's okay. But at the very base level, we have a signal that holds some sort of data attribute. By default, that's a NumPy array, right? But it could be a Dask array, it could be a CuPy array. It's something that's NumPy-like. And then we subclass that base signal in order to provide, either some sort of functionality or visualization tools that are specific to that particular type of subclass. So the most basic subclasses that we have are one-dimensional signals, which are things like spectra, and two-dimensional signals, which are things like images. So some things make sense to do on images, others make sense to do on spectra. There are other types of signals that have further things that might make sense. And so we have this hierarchy of classes that take care of all the functionality that we need for those. And then if you go even further down, we can have domain-specific classes that may make sense for if you have a certain type of spectral data, for example. It may make sense to do some sort of, in astronomy, some sort of processing to that type of spectra, but in EDS analysis, it makes sense to do a different type of processing for that spectra. So you can have domain-specific functionality just by sort of inheriting at the right place in this hierarchy of subclasses. And that allows us to have a really nice extensibility feature as well, where you can just subclass at the particular point in that tree that you need to provide the functionality that's needed. So HyperSpy builds on, of course, the scientific Python ecosystem. It's great. I really love this figure from the JupyterEarth documentation. We depend on all of these things at some point directly. We have other dependencies, of course, as well. Where does HyperSpy fit? When HyperSpy was first written, it was designed as an electron microscopy data analysis tool. So it lived pretty firmly in this domain-specific ring out here. Over the course of the past few years, a lot of effort has gone into trying to remove a lot of that domain-specific code and place it into one of a newly created extension to make the core of HyperSpy more domain-agnostic, while still having those extension packages that are able to provide the domain-specific functionality. So we're trying to work more towards the center. I don't think we'll ever go further down this little pie chart from here. I think that's the right place for HyperSpy. So briefly, the history of HyperSpy, it dates back to Francisco de la Peña's PhD work. It was originally called EELS Lab because it focused on EELS analysis. That's electron energy loss spectroscopy analysis. That's a type of spectroscopy that you do inside of a TEM. At this point, it was just like a lot of packages start like this, right? Just a collection of routines that he wrote that were pretty useful to him. And he started to see the structure emerging from how he wanted to deal with his data. At this time in this community, really the only way you could process your data was using a GUI package that had very significant licensing fees and license restrictions on it. And so this was an attempt to try to get around that because it's very expensive and grad students don't have any money, et cetera. Towards the end of his PhD, he added some more functionality, such as multivariate analysis, some signal separation, decomposition type stuff. He released the package onto GitHub as open source. Our initial commit was back in 2010, so we've been around for a minute. This was kind of the time that the first other users started coming on board, so other people started using the EELS Lab package. And Francisco was running tutorials in Paris where he was doing his grad degree, and then he moved to Oxford for his postdoc, and so started developing users at Oxford as well. The next year, the package was renamed to HyperSpy, which I think is a better name, and it more accurately reflects sort of the just general multidimensional data analysis functionality. The development team expanded a little bit to 3 from 1, so that's an improvement. And then also refactored to support actual n-dimensional data sets. At the time, it could only go up to 3 dimensions. That was all that was needed, but the model could apply to larger dimensionality. So what sort of things can you do with HyperSpy, and why might you want to use it? I'm going to go into each of these in detail, so I'm not going to stay on this too long. But visualization, lazy processing, curve fitting, model fitting, basic machine learning tools, input and output of scientific data formats, and then specialized tools for domain-specific applications. Those are kind of the high-level points. Why might you want to use HyperSpy? As I mentioned before, HyperSpy strives, and I think succeeds, at making it as easy to operate on multidimensional arrays of data as you would on single spectra or images. And that's a key aspect, is that you can develop an analysis pipeline for sort of in a simple case and then map it very easily in maybe a vastly distributed architecture on huge arrays to larger multidimensional data sets. You have access to everything in the scientific Python ecosystem, which is great, wonderful, awesome. Its modular structure makes it easy to add custom features if that's something you want to do. It We primarily operate in the Jupyter Notebook, Jupyter Lab environment. That's how most people use HyperSpy. That encourages reproducible and shareable analysis. This is kind of preaching to the choir here, I realize, but in the electron microscopy community especially, that was like a revolutionary way of doing data analysis that was unheard of at the time. And so that's really important for that community, I think. Also, it's free. As I mentioned at the time that HyperSpy was written, that was a very important consideration, that it was free as in beer and as in speech. Those were both very important and totally unknown to the EM community at the time. So what does the syntax look like? It's pretty straightforward, which is one of the reasons I really like working with it. You import the library, of course. You call the load function on a file. In this case, this happens to be the sort of standard EM proprietary data format, DM3 or DM4. And then you can call s.plot, and you get a nice plot using matplotlib and all the things that you might expect. There's a very concise syntax to slice and dice that data if you wanted to. So we have two slicer methods called isig or inav. Those represent slicing in the signal dimensions or the navigation dimensions as relevant. You can do that by calibrated axes units. So in this case, I'm saying I would like to take from 5 keV to 12 keV, the signal between those areas. And then, I don't know why you would do this ever, but I would like to reverse it. That's the thing that you could do. And then plot the resulting output. And in that one concise line, you can get a plot like that. For comparison, in the proprietary software at the time HyperSpy was written, to do this would take, I think we did it one time, it took like 35 lines of code. That was like a C-like scripting language, and it was very, very not nice to do. So this was a big improvement. And it still is. I still use HyperSpy all the time for all sorts of data. HyperSpy has interactive visualization of multidimensional data sets. So visualizing multidimensional data becomes very easy. You just use that same s.plot syntax, and HyperSpy will sort of automatically figure out, okay, what's the dimensionality of this data set? What's the best way I can display this? Up to about 4 dimensions, it makes sense how it displays it. After that, you start getting sliders and things. It's like it becomes hard to, inevitably display that many dimensions. But in case of a one-dimensional spectrum image, you get a little navigator plot where you can kind of browse back and forth through your navigation dimension here. If you had a 2D array of spectra, you get a similar little spectra picker that you can drag around and see the resulting plot. The cool thing also is that this navigator image, which is this one up here, that you actually navigate around, that can be totally customized. So if you were collecting multiple signals at one time, that's something that's done in the TEM all the time, if you could use a different signal source to navigate on. So if you have correlated data sets, you could do that sort of thing as long as they have correlated shapes, that you could navigate on one signal and see the resulting, the underlying data from a different signal. But HyperSpy makes it very easy to do that. HyperSpy also has named axes, so beyond sort of just the families of axes, like the navigation and signal dimensions, every axis also gets a name. This typically ends up being something like X, Y, and energy in the TEM world if you're doing spectroscopy, but those could be anything. You can get this nice HTML representation in the Jupyter Notebook for that. But you can edit any of these calibrations as you need. It's pretty easy to do that. You can access the axes by name. You can change their scale, their units. We can't do things in EV at NIST because we have to use SI units. So if you wanted to change it to joules for whatever reason, that's how you would do that. You can do both pixel-based or unit-based indexing. So if you use integers when you're indexing with HyperSpy, you'll get pixel-based, by pixel indexing. But if you use floats, you'll get calibrated unit indexing, and you can you can use those interchangeably, which is really handy as well. HyperSpy maintains lots of metadata about your data sets. That could be metadata that's read from the proprietary data format. So in the example of a TEM data set, you get a whole tree of metadata with lots of information about the condition of the instrument at the time that data set was collected. That's all saved in the proprietary data format, and HyperSpy reads that out, or rather, our new extension package, Rosetta Sci.io, reads that out. HyperSpy will also store information about the operations that it's doing inside of the metadata tree. So at the very basic, there's a file IO metadata node that will maintain information about what version of HyperSpy was used, what IO plugin was used to either load or save that data set, along with timestamps. So you have sort of a provenance tracking, which is nice. You can store information about the sample that is relevant to whatever operation you might be doing. So if you're trying to quantify atomic composition information, you want to know which elements are in that sample, all of that can get stored in there. And then all of the HyperSpy native data formats will preserve that metadata, so it survives round trips as you'd expect. We have two native data formats, HSpy, which is the older one, that's the HDF5-based format, and then ZSpy, which is ZAR-based, so you can use either of those. As I mentioned before, you can manipulate the dimensionality of your signal very easily using a NumPy-like syntax. If you just want to swap around your data axes, you can do s.t, right, and you'll get the transpose of your data set. You can do this in more, if you have more than just 3 dimensions, there's better ways you can do that. Just better specify which axis you want to switch where, but it's trivial to do that. We have built-in support for Dask, for big data using Dask. Most people that use HyperSpy, if they're doing it on their laptop, obviously things become slower when you're doing out of core operations and all of that. But it's pretty trivial to just add lazy equals true to most operations within HyperSpy, and that will automatically switch sort of transparently to using Dask behind the scenes. And so you don't, as a regular user, you don't really have to think about it unless you want to. But it provides an easy way of doing sort of big data analyses. There's curve and model fitting built into HyperSpy, so you can fit arbitrary models to your data set. So you can do this, again, HyperSpy makes it very easy to do this maybe on one spectra and then apply that to a huge multidimensional data set. You can use predefined components or custom components. This is actually a place where a lot of people choose to extend HyperSpy. They'll have a particular type of component that makes sense for their application. 2 examples down here would be EELS spectra or EDS spectra. Those have different spectral line shapes and all of this, and so you can have domain-specific model fitting. We also have some niceties in there. There's this SAMFire routine that was developed, which tries to use some physics-informed information about how the data is collected to to faster and avoid local minima in a multidimensional data fit. So there's some niceties in there, but you can use any optimizers provided by SciPy. It's compatible with sort of the whole ecosystem as you might expect. There's unsupervised machine learning capabilities built in. So this is what you might call signal separation or decomposition, clustering. There are various algorithms implemented to separate signals from one another to pick out which signals originate where within your data set. We have built-in support for PCA and NMF, as well as k-means clustering and a few others, but you can use any decomposition product from scikit-learn, can plug directly into HyperSpy. So these are just the ones that we've most people use. We provide the basics, but if you want to go down that road, you can get more into it. A good example of this is this paper I thought was pretty cool. This was a measurement, an EDS measurement in transmission mode of some core shell nanoparticles. So in the TEM, you're firing your beam through your entire sample. So if you're measuring something that's like a spherical shell around a core, there's at no point can you ever measure the pure spectra from the core of that nanoparticle, right? You're always going to be looking through the shell. So HyperSpy was used in this case to do independent component analysis, or blind source separation, sometimes it's called as well, to pull out the signal just from the cores of the nanoparticles themselves, separate from the shells, and then also separate from the background grid. So that was a pretty cool example of signal separation within a 3-dimensional data set. There's a lot of this sort of stuff that people do using HyperSpy, and it's really powerful for that. We also have a bunch of demos that can be done. Lots more. We have something like 1,200 references or citations on Google Scholar, so a lot of people are using this, particularly in the electron microscopy community, but it's growing in other communities too. I would like to talk a little bit about the community, some stats, 1,200 as I said. We have over 60 contributors over 14 years, so we're not a huge project, but we're not tiny either. And we've gone through kind of multiple waves of postdocs and grad students kind of supporting the project, so it's got some staying power past, if your cadence is longer than the typical PhD, I think you're a successful project in the sense that you've survived, right? Someone's PhD length. So we're well past that. I think we're pretty mature in that regard. A lot of packages are depending on HyperSpy too, which is really cool to see. One of the core aspects of HyperSpy that I like to focus on is the community-driven development aspect. So since the beginning, HyperSpy has been written by users for the users. There's never been corporate sponsorship or anything like that. Not that any of those things are bad, but that's just not how HyperSpy has grown. HyperSpy has always put a focus, and this really comes from Francisco from the beginning, has always put a really good focus on documentation and sort of code style and all of those sorts of great things that help to lower the barrier for contributions, which I think is, a lot of those 60 contributors have maybe contributed one or two little things here and there that they needed the package to do. By lowering that barrier of entry, we allow people to be able to do that. We have an interactive chat room and GitHub discussions and all the sort of typical community things that you might expect. And we also do regular sort of in-person and virtual tutorial sessions. We've done this at the Microscopy and Microanalysis Conference a number of times. We also run summer schools and those sorts of things. If you're interested in those, probably our news section of the website is the best place to keep track of that. Just a personal side about kind of what the community has meant to me personally. When I was an undergrad, I did some computational material science, started figuring out what Linux was. When I was a grad student, I was doing electron microscopy and thought, oh, well, there's this other way people can look at their data, and that uses Python, and that sounds pretty cool. I've never used Python. What is that? Interesting. And basically, I can trace back a direct line from that moment to like where I'm standing today, right? Which is I'm gainfully employed at a national lab doing Python and data science and all of those things. And really, that comes from learning how to program as part of a welcoming community that also had high standards, right? So I started as a know-nothing grad student, started learning how to code, how to write documentation, all of that. And yeah, it makes it really powerful. This is my first SciPy, though, so maybe I shouldn't have waited that long. That's what I've learned. It's been a really cool and inspiring week of seeing really awesome projects. HyperSpy now has a pretty wide community and ecosystem of packages that are extending it. And I realize I'm out of time, so I'm going to jump a little bit further. Just to say that prior to 2.0, HyperSpy had a lot of that domain-specific code still in it. We did a lot of work recently to kind of extract those out into their own extensions so people can, to make it even easier to continue developing HyperSpy for the future. And yeah, I guess didn't want to mention this. We were very similar to X-Ray. There's a really great discussion thread that has really kicked off in the past 7 hours of the X-Ray maintainers and the HyperSpy maintainers. So there's probably potential for future collaboration there. And yeah, just some parting thoughts. Thank you. Sorry for running over.
Thank you, Josh. Do we have any questions?
Can you comment or say anything about extending HyperSpy to support custom data formats to load data easily if it's not one that you support?
Yeah, so I have somewhere here. This is not exactly, anyway. So we have a number of formats that we do support out of the box. Those mostly come from the electron microscopy world because that's where we were born. One of the packages that we split into as part of this was, we thought this was a clever name, Rosetta Sci.io, and this little icon is the Rosetta Stone. It aims to be this translation layer between, so that would be the place to contribute one of those. And then if it is part of that, there's sort of one common load interface that we expect every reader to implement a certain sort of structure, and as long as it can return an array with a little bit of metadata attached to it, it will be able to be loaded into HyperSpy. But I often, even if there's something that isn't built into HyperSpy, as long as you can get it into a NumPy array, you can put it in a signal in HyperSpy. You won't get all the nice, domain-specific functionality for that particular thing, but for just prototyping something, I've done that all the time where, as long as you can get it into a NumPy array, you can work with it in HyperSpy.
Okay, I think we have time for one more question, if we have.
So just a really quick question. I enjoyed your presentation. Do you support 3D rendering of volumetric data?
Oh, I guess you're using the mic. Do we support volumetric rendering of three-dimensional data? We did, and nobody used it, and so we removed it because it had it depended on some projects that were abandoned over time. And so currently no, but building that in or building an extension to do that would probably not be too hard. There are plenty of options that do that in the Python community. So But built into HyperSpy directly, no, other than sort of the two-dimensional projections that I showed before.
All right, thank you. Thank you, Josh, and
Thanks.
thank you once again.